Okay, good morning class. Today we are going to learn about the consolidation. So first point is compressibility. It is the property due to which reduction in volume occurs under compression. Now what do you mean by compression? So compression means whatever your material is getting compressed with respect to your load applied. So whatever load of the structure is applied on the head of the soil, on the surface of the soil, what happens is it tries to compress, as soil is only a compressible member. Soil is not a tensile member, it is a compressible member, so it will try to compress and the volume will reduce. So if you have an impact loading, then what will happen? Removal of air will take place, but by its own weight gradually, if the soil is reducing or compressing, then water will evaporate. So water will be taken out. So that part is known as your consolidation. So in soils, compression takes place due to compression and expulsion of air in the voids, expulsion of water in the voids. So what first part is your compaction, removal of air, and next part is your consolidation, removal of water, both from the voids. The compression of solid grains and compression of water in voids are negligibly small and are neglected. It says that there are small soil grains. So when you have a compressive force, then the water from the voids will get out and the small area will be generated, that is neglected. So consolidation, it is the compression of the soil mass due to the expulsion of water from the voids under a steady static long-term pressure. It is not an impact force, it is a gradual force, gradual pressure, gradual load which is taking place, and gradually when soil mass tries to compress itself, reducing its weight, its what you can say, its volume, then what happens? The expulsion of water takes place under steady static and long-term pressure. Compaction, compression of soil mass by expulsion of air from the voids under short duration moving or vibratory loads. It says that whenever you are having any type of a sudden loading, then what happens is the voids which are present there and the air present there, then it will try to expel out the air and it will reduce in the volume. So sudden compaction was good. So what happens is sudden compaction is just because of the sudden loading, and since the sudden loading is there, then what happens is your removal of air takes place. Next is factors affecting consolidation or compaction. First is your for coarse grain soils. So coarse grain soils, first is sand, one is permeability and another is drainage condition. Then for clays, in addition to above, expulsion of double layer water from grains, slipping of particles to new positions of high density. Compaction is a quick process, whereas the consolidation is the slow process and time bound. So it means that compaction is because of the sudden impact loading and consolidation is the gradual loading. So with respect to the gradual loading, expulsion of water will take place, and with sudden loading compaction, that is expulsion of air will take place. Now here the stages of consolidation: initial consolidation, the reduction in volume just after the application of load. In partially saturated soils, it is due to the expulsion and compression of air in the void. Partially saturated soil means 50% of saturation. So its degree of saturation is 50% and 50% it is dry. That means sudden compression, if you are giving impact loading is giving, then it will only remove air from the void. Primary consolidation, the reduction in the volume soil due to the squeezing out of water from the voids in terms of primary consolidation or primary compaction or primary time effect. Because of the sudden loading, some amount of water will be removed from the soil, and that is known as your primary consolidation. Next is your secondary consolidation or creep, is the compression due to expulsion of highly viscous water and placement readjustment of solid particles. Once after the reduction of all the excessive water pressure to zero and primary consolidation is completed, secondary consolidation occurs under constant effect. Stress is very stress is at very slow rate, also called secondary compression or secondary time effect. It says that when the reduction of water at sudden compaction or compression is done, then the secondary consolidation takes place, which is having the stresses developed in the soil mass. It is proportional to the logarithmic of time. Secondary consolidation occurs only in case of organic soils and loosely deposited clays. Kazaghi's theory is not applicable in secondary consolidation. See, look here, what happens is whenever you are having the cohesive soil, which is highly sensitive, highly cohesive, highly expansible soil, then what is happening is these organic soils and clays will have the water molecule inside and you have the impact loading on it, then initially and primarily it will reduce water, but it will take some time for expulsion of total water from the bed of soil mass. So therefore that part is known as your secondary consolidation. And Kazagi's spring analogy is not applicable for it because it is only for the primary consolidation stage. Now, what we need is Kazagi's piston and spring analogy model. Here, what happens is comparison is taking place between the molecules. Now you can see this diagram. If you are applying the load, there is a soil and water inside, and there is a spring inside, and there is a air valve inside. Firstly, if you keep it closed, then what is happening is when the load is not applied, it will remain as it is. But when you apply the load, the spring will try to compress. When the spring will try to compress, the water molecule will try to go up, and when you open the valve, it will go out. So it is saying that how much load you are applying, that maximum compression will take place. So firstly, for this condition, soil grains, that is taken as spring, void when water in the cylinder, permeability when valve is opening, effective stress in the soil, then load on the spring, and excessive pore pressure load on the water. So this is what is taken. That means here the spring is acting as a soil grain. Voids and water are present here in the cylinder. Then permeability, drainage of water is through this valve here, and effective stress in the soil. The load you are applying which gives you the excessive stress on the soil, and excess pore pressure, the load on water, what is to be taken. Now, 7 point is excess hydrostatic pressure or excess pressure, pore pressure. It is given by U bar. So it is the pressure that builds under pore water of a saturated soil mass due to external applied loads, also called as hydrologic or hydrostatic dynamic pressure. Whatever load we are applying from the external side, then that load is known as your hydrostatic load. Hydro respect to water, static means at rest position. Next, if you can see hydrodynamic lag, if there is any reduction, if there is any slowdown motion, if there is any error, then it is known as hydrodynamic lag. It is the daily cost delay caused in consolidation by the slow drainage of water out of a saturated soil mass. Now what happens is the when you are applying the load, the water will try to drain out. But sometimes it happens that if there is no excessive load and if load is there also but water is not expelling out whatever is required from the 100% saturated soil, then this delay of consolidation can lead to your lag, which is known as a hydrodynamic lag. As water escapes out from the soil during consolidation process, excess hydrostatic pressure decreases, the effective pressure on the soil increases, void ratio decreases, and degree of saturation remains same. So what happens is degree of saturation remains same means 100% degree of saturation water is present in the soil, but it is reducing your void ratio, it is having the decrease in pressure, all things are decreasing with respect to your loading, but saturation remains same. At equilibrium, that is after completion of consolidation, the applied pressure becomes equal to the effective stress, the excess pore pressure becomes zero. That is when we say that the total geometry is balanced, that is there is consolidation has also taken place, there compaction has also taken place. So what happens at particular level, the total value comes to zero. That means excessive stress has been already developed, and that part is known as your excess pore pressure, which is zero. Then consolidation of laterally confined soils. So if you can see the graphs here, so first graph, this is sigma dash stress versus strain. So it is a curve like this, smooth curve. So when you plot loading, when you have a stress versus strain, then it will give you the diagram, then it will give you the stress and it will give you the strain also. Here also, if you plot a logarithmic scale diagram or graph, then you get a log stress dash with respect to your strain, then you get a straight line, and if you plot a graph, then you will get CC, compression curve. Then here again, if you see that this is your loading, then with respect to your loading, you are increasing the compression, then again it is coming out, then recompression is taking place, then again it is reducing. That means first virgin compression curve at the initial stage of the loading, then it will come to compression, then there will be expansion of soil again, then there will be recompression, and when it comes to this position, then your curve between stress and strain is calculated. So how it is calculated? For compression, E0 at initial stage, void ratio at initial stage, minus EF, void ratio at final stage, equals to delta E equals to CC, compression curve, log to the base 10, in bracket sigma dash F upon sigma dash 0, where sigma dash F final stress, sigma dash 0 initial stress. So here CC is the compression index, slope of linear portion C log to the base sigma dash curve, E0 initial void ratio at sigma 0 dash, EF void ratio at final increased pressure sigma F dash. So you can calculate by this formula given by symptom Cc equals to 0.007 WL minus 10%, where WL is your liquid limit for remolded soil. Okay, so what do you mean by remolded soil? You are excavating the bad soil and then again you are dumping it with some stabilizing material, or simply you are dumping and compacting it. So that is known as a remolded condition. Next is the CC equal to 0.009. So this is WL minus 10% for undisturbed soil sample and field consolidation given by Tarzagi and Tag. So it means this is again your liquid limit. So undisturbed soil sample means we are not modifying the initial properties of soil with respect to some borings, and using samplers you can extract the soil which are retaining its initial properties. So that is known as your undisturbed soil sample. Next is your coefficient of compressibility AV. So AV is given, it is the ratio of decrease in void ratio per unit increase of pressure. So that is given by AV equals to delta E upon delta sigma dash. So AV is given by E0 minus EF upon delta sigma dash. Unit is meter square per kilonewton. Okay, so this value is dimensionless, no unit strain, and this is having the unit kilonewton per meter square, so it will become meter square kilonewton. So AV is not constant. As pressure increases, AV decreases. Now coefficient of volume or coefficient of volume compressibility MV, it is the change in volume of soil per unit of initial volume due to unit increase in pressure. So MV is given by delta V upon V0 dot delta sigma dash. Again here unit is meter square kilonewton. For laterally confined soils, MV equals to delta H upon H into delta sigma dash. So substituting all these value, you will get MV equals to AV upon 1 plus E0. Consolidation settlements SS, SF, delta H with respect to MV into height into delta sigma dash. So delta H is given by delta E upon 1 plus E into total height. SF therefore is given by H upon CC upon 1 plus E0 log to the base 10 sigma F dash upon sigma 0 dash. So FH is the height. Therefore sigma dash is initial plus total sigma dash. So therefore SF is taken as HCC upon 1 plus E0 log to the base 10 with respect to your initial and total sigma dash stress, where H is the initial thickness of clay layer undergoing consolidation. CC is coefficient of compression index of the clay, which is given by this formula. E0 is the original void ratio of the clay undergoing consolidation. Sigma 0 dash original effective pressure at center of clay layer. Delta sigma dash increase in pressure at center of the clay layer due to applied loads. This is most important since you are having the axial loading. Axial loading means on the center vertically downward load. So that is the vertically downward load directly applied on the field. So that is what you have to take into account. So we'll see one example here. A footing for a water tower carries a load of 900 tons and is 3.6 meters square. It rests in dense sand of 9-meter thickness overlying a clay layer of 3-meter depth. The depth of foundation is 1.5 meter. The clay layer overlies hard rock. Liquid limit of the clay is 54%. Void ratio is 1.08. The saturated unit weight of the sand and clays are 1.89 ton per meter cube and 1.79 ton per meter cube respectively. Assume the load distribution as 2 vertical to 1 horizontal. Assume that the site is flooded, 100% saturated. Flooded means 100% saturated. Determine number one, the ultimate settlement due to the consolidation of the clay layer, and second is the maximum effective stress at the center of the clay layer at the end of the consolidation. So footing is given here. So footing, if you can see, this is the footing which is having Q equals to 900 ton given. Then you are having and is 3.6 meter square. This width is 3.6 meter. Then it rests on dense sand of 9 meter. So this is your 9-meter sand and overlying layer of clay 3 meter. So this is your clay layer of 3 meter. The depth of foundation is 1.5 meter. So this from ground level to the base of the footing it is 1.5 meter. So the clay layer overlies hard rock. So here is the hard rock and the clay layer is above this. So unit weight, saturated unit weight, sigma gamma sat for sand is 1.89 and for clay it is 1.79. So you need to calculate the settlement as well as the stress. So WL liquid limit is 54% given. Initial wide ratio is 1.08. Height is 3 meters. Okay. Then CC equals to point by applying formula 0.009 WL into 10. So 54 is your liquid limit. It gets you 0.396. Then sigma dash initially 9 gamma dash. This is your height or thickness of the sand plus 1.5 gamma dash. This is your foundation there. So 9 into 1.89 minus 1. Okay, minus 1 because initial length you need to take. It is 1 here given. Plus 1.5, 1.79 again minus 1. So this will give you 9.19 ton per meter square. Delta sigma dash total load upon B plus Z square, where B is your width of the footing and Z is the from the base to the clay layer. In between center of the clay layer is your Z height square. So Z will be your 9 minus total 9 minus 1.5. So that will be your 1.5 plus 1.5 is your this center of your clay layer. Okay, so total will be 9 meter. So sigma delta sigma dash is calculated. Then stress at final condition will be stress as initial plus total average stress. So it will give you 14.86. So therefore settlement SF will be calculated by this formula which is coming to you as 11.9 centimeter. And total effective stress final sigma dash this plus this will give you 14.8 ton per meter square. Okay. So second example for the clay layer shown in figure MV equals to this much. If the earth fill of the unit weight 20 kilonewton per meter cube and 2 meter depth is dumped on the clay layer, then the ultimate settlement of the clay layer is dash m. Very simple it is. Firstly, you have to see the diagram. So it is having a saturated clay, then you are having a sand. It is given as 3 meter and the load is applied. So MV is totally given to you. Gamma unit weight is given to you as 20 kilonewton. Height H is given to you as 3 meter. So directly you have to apply formula of settlement SF equals to MBS delta sigma dash. So delta sigma dash you need to calculate gamma into 2. Okay. So this 2 meter depth is given to you. Okay. So 20 into 2 will give you 40 kPa. And SF now you have calculated it is in meters, so convert it into mm. Okay. So 13 point consolidation of undisturbed specimens. Based on the history of loading, soil deposits are divided into three classes. So pre-consolidated or pre-compressed or over-consolidated soil. If a soil has effectively being subjected to a pressure in excess of initially present overburden, it is said to be over-consolidated. Normally consolidated, the soil which have not been subjected to a pressure greater than present existing pressure and which is also completely consolidated, then the existing overburden is called as normally consolidated. So there is not much difference. The pressure in excess then presenting existing pressure. Okay. Under consolidated soils, if a soil, clay soil, has not reached equilibrium under the applied overburden loads, then it is said to be under consolidation. Under consolidated, so area of the recent land fill. Normally consolidated soils and over consolidated soils are not different types of soils, but these are conditions in which soil exists. The recompression index CR, it is very small compared with compression index CC. The soils in the over consolidated state have small compression. The settlements of the structures built on over consolidated soils are small. As the consolidation has already taken place from primary to normal consolidation, then under consolidation. So all these stages have been passed. Then what happens? The compression of soil, because it has reduced in volume already. No other such reduction now will take place, and it will be very, very small if the reduction or compression of the soil takes place. So that is the condition of your over consolidation. So over consolidation OCR is given by sigma C dash upon sigma dash, where sigma C dash is the maximum pressure to which an OCR clay had been over consolidated clay had been subjected to consolidated in the past and pre-consolidated stress. Consolidated means when you apply load and the compression takes place, and if the load is reduced, then it will not come to its original position. But if the load is reduced and the soil somewhat at some stage comes to its original position, then you can say that it is reconsolidated stress. So for OC over consolidated clays, OCR is greater than 1. Normally consolidated clays, OCR is equal to 1. And under consolidated state, OCR is less than 1. So Tarzagi's theory of one-dimensional consolidation, there are some assumptions. The soil is homogeneous, isotropic, fully saturated, soil particles and water are incompressible, consolidation occurs due to expulsion of water from the void, Darcy's law is valid, soil is laterally confined and consolidation takes place only in vertical direction, drainage takes place in vertical direction, AV, MV, K are constant. So all these things are has to be considered, and Tanzaki has considered when he has decided to calculate what is the consolidation. So first, delta U bar upon delta T equals to CV, delta square U bar upon delta Z square. So what is delta U bar upon delta T? It is the rate change of excess of pore pressure with time. Then delta square U bar upon delta Z square equals to rate of expulsion of pore water pressure with depth Z. CV is the coefficient of consolidation given by K K upon mv into gamma w unit weight of water, K equals to coefficient of permeability, and units of CV are m square upon second or centimeter square per second. Solution of the above differential equation gives time factor TV, degree of consolidation U. Kindly have a look. Okay. So what is time factor? TV equals to CV into T upon D square. So what will happen? Where T is time for consolidation, D is the drainage path, single drainage or double drainage. So D equals to H for single drainage, half closed layer. D equals to H by 2 for double drainage, open layer. For the same degree of consolidation, TV is same. Hence, T is directly proportional to D square upon CV. If CV is assumed to be constant, then T is directly proportional to D square and D may be single or double drainage. Hence, T1 upon T2 equals to D1 upon D2 whole square. So, degree of consolidation is U equals to settlement at any time by ultimate settlement into 100. So, U equals to S upon SF into 100. Now, degree of consolidation U. So, U equals to ratio of dissipated excess pore water pressure to initial excess pore water pressure. Then it is given by U equals to Ui minus U upon Ui bar into 100, where Ui bar is initial excess pore water pressure and U bar is the pore water pressure exists at any time. Anytime the water can increase, anytime the water can reduce. So whenever the excess water is there, then your pore water pressure will increase or exist. For U less than or greater than 60%, TV equals to pi by 4 U percent upon 100 square. For U greater than 60%, TV equals to 1.781 minus 0.933 log to the base 10, 100 minus U percent. Let us see some example. So a 2 meter thick clay layer has CV equals to 2 into 10 raised to minus 4 centimeter square per second. If a building is constructed on it, how long will it take to attain half the ultimate settlement under double drainage? For half settlement, U equals to 50%. Alright, it is said to be half, attain half, so U equals to 50%. So TV for 50%, what you are going to do? Pi by 4 U square. So pi by 4 into 0.5 whole square will give you 0.196. So D equals to H by 2. Double drainage is mentioned, so it will be H by 2. So height is 2 meter thick is given, so 2 upon 2 equals to 1 equals to 100 centimeter. Therefore, TV will be CVT upon D square. So we have calculated 0.196. Substitute the value of CV. T you need to calculate. Here D is 100 square, so T is calculated in seconds, then converted into days. Then isochrones, the curve indicating the distribution of excess hydrostatic pressure, the hydraulic gradient at any point is equal to the slope of isochrone at any point. Isochrone curves are mentioned when you plot a graph, and at a particular slope, hydraulic gradient h upon L, okay, where h is height and length is the length of soil sample. then that slope is needs to be said as isochrone. Determination of coefficient of consolidation by time fitting methods. Square root of time fitting method, logarithmic time fitting method. Total compression. What is total compression? From the given diagram, it is initial compression first, then primary compression, and third is your secondary compression. Totally, one by one, when it takes place, then what happens is the total compression will take place. So first part is floating ring cell or odometer. Okay. So we haven't done this consolidation test in GT1 since it was not in the syllabus. But the apparatus used is consolidometer and odometer. If you do MTech post graduation in soil mechanics, then you will require to do the consolidation test also. So first part is floating ring cell type. Both top bottom porous stones are free to movement compress the soil. Fixed ring cell type bottom porous state remains stationary while top stone moves. यहाँ आपको ऐसे फिटिंग करनी है कि दोनों ऊपर का नीचे का स्टोन सॉइल के साथ में जो है वो मूव हो. यहाँ हम फिक्स कर देते हैं और एक मूविंग पोजीशन पे रखते हैं. The floating ring cell has the advantage having small effects of friction between the specimen ring and the soil specimen. Direct measurement of the permeability of specimen at any stage of loading can made only on the fixed ring type. So these two conditions can only be applicable if you have second type of test. Okay, condition. Determination of void ratio at various level increments during consolidation. Height of solids method applicable to the oversaturated and unsaturated soils. So HS equals to WD G gamma W into A. Void ratio at initial stage E0 equals to H minus HS upon HS. Void ratio at any stage, initial stage, this is any stage, then HF minus HS upon HS, and HF is given by H minus delta H. So we'll see here what the terms are said. If we have the change in void ratio, then this formula is applicable for saturated soils. Delta E upon 1 plus EF equals to delta H upon HF. So where A is the cross-sectional area, here this A is cross-sectional specimen height, total height, this H. HF height of at any stage, this one, which is given by H minus delta H. Delta E change in void ratio. Delta H equals to change in thickness of the sample. EF equals to final void ratio. HF equals to final thickness of soil. WF is the final water content of the soil sample. And EF is calculated by WF into G, where G is the specific gravity of soil. By having this, you can calculate, this example is given, so you can calculate the HS and E0. Then intermediate settlement, elastic settlement, all highly permeable soils undergo intermediate settlement. Intermediate settlement also occurs in fine grained soils. So it is given by as I, Q and B, 1 minus V square upon E into I. So Qn is the net intensity contact pressure. Okay. B is the least lateral dimension of the loaded area. E is the undrained modulus of elasticity. I is the influence factor, depends on the rigidity, shape of the loaded area L by B ratio. And V is the Poisson's ratio of the soil. So influence factor for vertical displacement due to elastic compression IS 8009 part 1 is given by this. Alright, the shape is given if you are having the flexible pavement, if you are having the rigid pavement. When you are having the flexible, you have three parts: center failure, corner failure, and average failure. So circular, rectangular, L by B, 1, 1.5 and 2. So these are the values which are given or taken, obtained. So by these values, you need to solve these numericals. Footing is 3 into 2, exerts a pressure of 100 kN per meter square on a cohesive soil. ES equals to 5 into 10 raised to 4 kN per meter square and mu equals to 0.5. Determine the intermediate settlement at the center, assuming the footing is flexible, the footing is rigid. Take the influence factor for the flexible footing as 1.3 for L by B ratio of 1.5. Everything is given to you. L is 3, B is 2, Q and loading is given to you as 100 kilonewton per hour. ES is given to you, mu is given to you. So only substitute values and get the answer. Okay. So after doing this, complete the consolidation part here. Next is your next topic. If you can see, then that is the compaction. So few compaction part will do, and in next class we'll again continue. So compaction, we have already seen that removal or expulsion of air is known as your compaction. So it is the compression of soil mass by mechanical means to improve engineering properties. It is due to the escape and compression of air present in the soil mass. Volume reduction occurs due to the escape of air under short-term loading under constant water content. See, compaction is very easy to understand. Mechanical means mean impact loading to improve the engineering properties of soil. What do you mean by engineering properties of soil? Engineering properties of soil means you are increasing its permeability, you are increasing its strength. So these properties are there which you are increasing. So by this, we can increase lot many values. Strength property, C5 ratio if you are having, then you are calculating permeability. The permeability is also taking place. So all these things you have to take care of. Next is volume reduction occurs due to escape of air under short term loading under constant water contained. Permeability, void ratio, compressibility decreases, shear strength increases. Compaction tests are done to determine amount of compaction and optimum moisture content OMC. When you plot a graph between stress versus strain, then you need to get ultimate dry density, gamma D, and optimum moisture content. You plot a graph between water content and dry density, then you get the value like this. Okay. So Indian standard light compaction test similar to standard Proctor test. Test result used for highways, embankments, canal banks. Mold volume is 1 liter. Soil in 3 layers. Each layer is given 25 blows. Hammer weight 2.6 kg and height of fall is 31 centimeter. So this is one Proctor test, Proctor apparatus. So Proctor apparatus is having some round mold. You have to take soil in 3 layers and each layer you have to give number of blows by the hammer. Indian standard heavy compaction test similar to modified Proctor test, results used for modern express highways and runways. Mold capacity 1 liter, soil in 5 layers, each layer 25 blows, hammer weight 4.9 and height of fall is 45 centimeters. So it depends upon which type of test you are carrying. If you are carrying Proctor test, this is the dimension and required apparatus. If you are going for modified proctor test, then you have to take this apparatus. The compactive effect in the modified proctor test is about 4.55 times than that in standard proctor test. So you can see how huge difference is there between modified and standard proctor test. If percent soil retained on 4.75 mm ISP is greater than 20%, large mold of capacity 2.25 liters is recommended. In such case, number of blows per each layer shall be 56 for both SPT and MPT. SPT is standard process test and MPT is modified process test. So when you can plot a graph, if you are plotting a graph between water content and dry density, if you do standard proctor test and you plot a curve, at the peak point you get sigma gamma dash max, and at the peak point you get OMC, optimum moisture content. Similarly, if you do the test of modified proctor test, you again get a curve, and at that curve you can also plot gamma D max and optimum moisture content you get, and further you calculate gamma D, then you get a zero air void line which says that 100% saturation line. If such type of curves occur when you do all these tests, then if this is the curve, then highly plastic. If this is curve, low plastic, clay. If this is low plastic silt, and if this type of curve occurs, then it is well graded soil. Then dry density gamma D is calculated by this formula, and equation of zero air void line is calculated by this formula. Gamma D equals to gamma Wg upon 1 plus gamma Wg. Then what are the factors which are affecting compaction? So water content, as Wc increases, the gamma D increases, reaches maximum value and then decreases. So it means that if you are increasing the water content, then your dry density is also increasing. Okay. Amount of compaction, as compactive effect increases, gamma D increases, or optimum moisture content decreases. Type of soil, pure sand, does do not have well defined OMC. Soils compacted dry of optimum have more swelling and more shear strength. Soils compacted wet of optimum have low swelling and low shear strength. So this is the condition when dry and when wet. Then placement water content. It is water content that is usually used in the field for compaction. Under pavement floors and for core of earthen dam, the soil shall be compacted wet of optima to avoid large expansion and swelling pressure. For highways, embankment, and for outer swells of earthen dam, soil shall be compacted dry of optimum to have more strength and less compressibility. If there is pavement, then wet of optimum can be done. But when you are having the highways or earthen dams, then you have to be more prominent that there is a dry condition, so that you get heavy strength, high strength. Compaction equipment, tampers for compacting in confined areas like trenches, behind bridge, abutments, etc. Smooth wheel rollers for granular soils to provide smooth surface at the end of days work to quickly drain off rainwater. Pneumatic tired rollers for cohesive and non-cohesive soils, seafood rollers for cohesive soils, clays, vibratory compactors for granular soils, for sands is the best method. Relative compaction, dry density in field upon maximum dry density obtained in the lab into 100. So Proctor needle, plasticity needle, it is punched by 7.050 centimeter in the soil to know the penetration resistance, thereby the placement, water content and dry density. So this is how your compaction complete. If you have any questions regarding consolidation and compaction, so you can ask me anytime. In next class, mostly tomorrow, we'll start with the shear strength parameter. So if you have any doubt, you can ask, or otherwise, thank you so much.